Alrighty, welcome, ladies and gentlemen, boys and squirrels.
Huh?
We are continuing in our conversation about you are a squirrel. Yes. Little nose, big ears.
He's talking about all the girls. Yes,
Okay.
just you.
Um,
Boys and squirrels.
Yes.
It's plural,
Little
not
girl.
singular.
Okay. So that's fine for all posterity. That was Janine, by the way.
Hi, next class.
Okay. Electromagnetism is our conversation today. And we are going to be talking about the way that the electric force, which we have been talking about in the past, is related to the magnetic force. And they are relatives of each other. They create each other. They work together, which is why there are things like electromagnets, where you can pass an electric current through something and it turns into a magnet. And so the electromotive force and the magnetic force are different aspects of the same phenomenon. And we're going to be looking at that today. Electricity, as I just said, electricity and magnetism are different ways of looking at the same force, and they can cause one another. So some examples. If you pass a conductor through a magnetic field, you get an electric current. So I have some really weak, sad little magnets here. And if I were to take a wire, this is not a wire.
It's a rubber band.
It's a rubber band, but we're going to pretend that it's a wire. If this were a wire and I were to go like this, then I would be causing there to be an electric current through the wire as I move the magnet through. It's kind of strange. Or if this were a wire, and I were to wrap it around a piece of metal and pass a current through the piece of metal, I would have just made a magnet where there hadn't been a magnet before. So magnetism and electric fields cause one another. They influence one another and they cause one another, which is very handy for us because we can make electricity by moving magnets, which is what a generator is. Or we can move magnets by passing electricity through a wire, which is what a motor is. And so we use both of these relationships a lot. Okay? Electricity and magnetism, two aspects of the same thing. And when we study this again next time in physics, so in 4 years from now, you'll come back to this concept. And you'll go much more into detail with it, and you'll learn about the orientation of the electric fields to magnetic fields and all that kind of stuff. But for now, we're just introducing you to the subject, kind of hitting the highlights. I see some pencils still moving, so I'm going to pause here. So this is an example here. We have a piece of metal attached to a wire and a light bulb and another wire completing the circuit. So this metal bar is just part of a circuit that goes through this light bulb. And if you take the metal bar and you wave it through the magnet, the light bulb will flash. And I could have set this up for you, but I didn't. But here's a picture. It doesn't help if you just hold the bar in the magnet. Then the light bulb will flash when it comes in, but it won't light anymore while it's sitting there. You have to like wiggle the bar through the magnetic field. The magnetic field has to be changing. And while you do that, as the bar is going through a changing magnetic field, the light will flash. It's kind of cool. So moving a conductor through a magnetic field creates electricity, and the opposite is true. Getting a current through a conductor makes a magnet. And so magnetism causes electricity, and electricity causes magnetism. They are yins and yangs, and tops and bottoms, and left and rights, and whatever you want to think of, related items, related ideas. There is this thing called the right-hand rule. So if you grasp a wire, and we'll pretend that this thermometer case is a wire, grasp it with your right hand so that your thumb points to the negative pole of an electrical circuit. Magnetic field lines will form in the direction indicated by your fingers. So if this were a wire,
Are we going to try that?
you're going to do a little bit of experimentation with that tomorrow, yes, but not. You're doing it the other way around. You're seeing the magnet and electricity. But anyway, here we have a conductor. I'm going to pretend this is a wire. And if you grab the wire so that your thumb points to the negative pole, the negative part of the circuit. So if this were a wire connected to a battery, this side goes to the negative pole of the battery, and this side goes to the positive pole of the battery. Your fingers of your right hand point in the direction of the magnetic field lines. They curve around the wire in the direction that your fingers go on your right hand. Now, those of you that are left-handed, I'm sorry,
No.
the universe does not have a left-handed rule.
What?
The universe doesn't like left-handed people. No, I'm just kidding. But it was made with a right-hand rule, or at least we've explained things with the right-hand rule, right? Where if your thumb points to the negative, your fingers go the direction of the field lines. And so this is a rule that you can use anytime you've got to figure out which way does the magnetic field go. Picture the wire, see which way the negative direction is, and then try to, in your mind's eye, grab the wire. Maybe not always a good idea to actually grab the wire, because maybe that would hurt you. But pretend to grab the wire with your right hand and be like, thumb to the negative, field lines go this way. Thumb to the negative, whichever way that is, field lines go this way, right? So that will help you as you are looking at the relationship between the direction of the electric field and the direction of the magnetic field. So you can notice something about that if you just, hold your right thumb up like you're hitchhiking, which you should never do because strange people pick up children who are hitchhiking. But anyway, pretend you're hitchhiking, right? The electric fields go this way. Magnetic fields go this way. So generally speaking, magnetic fields are at a 90-degree angle to electric fields. And you'll see that in physics next year. We'll get much more into detail with that. But electromagnetic waves, the electric potentials travel this way. And while they're traveling this way, the magnetic potentials travel this way. And so it's this like, ooh, back and forth snaky thing that goes through space. And it's all based on the right-hand rule. So electric fields and magnetic fields are 90 degrees opposed to each other and create each other as they go through space. So this relationship between electrics can make magnets and magnets can make electrics is the basis for how we generate electricity. Generators and motors are exactly the same piece of apparatus. Generators and motors are exactly the same piece of apparatus. The only difference is whether the power is being generated or consumed. So I don't know if you've ever noticed this, but if you could take a motor that spins when you hook it up to a battery, and it spins, right? And then you can hook that motor to another motor, no battery involved, just one motor hooked up to another motor. And then if you spin the first motor manually, the second motor starts to turn. It's the weirdest thing, because you're generating some electricity in one motor, and that electricity is causing the second motor to turn. So this is actually the reason why hybrid cars work, because there's a motor attached to the wheels, and the battery of the car can make that motor turn and drive you along the road. But then when you take your foot off the accelerator and the car is coasting, all of a sudden that motor turns into a generator and uses the energy of the spinning wheels to recharge the battery. It's the same piece of apparatus. You don't have a generator separate from a motor in a hybrid electric car. It's one piece of apparatus, and the thing is either causing the car to move forward, or it's sucking power away from the wheels and using the momentum of the car to generate electricity put back in the battery. Okay? So a motor is electrical power causing magnetic field, which causes motion. A generator uses motion to manipulate a magnetic field to create electrical power. So it's the exact same thing. It's just, is it making motion or is it making power? Which means that you could take these huge turbines in dams and things of that nature that generate a ton of electricity, and if you were instead to put power into those things, they would spit water out of the dam really fast. It's the same piece of apparatus. A generator and a motor are the exact same piece of apparatus. Here's some pictures for you. Here's some pictures for you. This thing is a what? Generator or a motor? I'm not sure. Here we have a bunch of magnets on a central bar, and there's wraps of wire that go around here. And in the cutout made so you can see this, you can see the wire here, and you can see bundles of wire that wrap this way. And so if I were to turn this with some outside force, I would be changing the magnetic field through which this wire passes, and this would be a generator. Or I could instead pass electricity through these bundles of wire, and that would cause a moving magnetic field which would spin these magnets and drive this thing. So I could either consume electricity and produce motion, or I could consume motion and produce electricity. It's the exact same piece of apparatus, okay? DC motors and generators are the same thing. This is an old school, very, very early motor / generator. And here we have a bar that is wrapped in wire and a magnet spinning in between, okay? And I can either pass an electric current through the wraps of wires and make the magnet spin, or I can spin the magnet and get electricity out of the wires. Either or, okay? Now you can't do both. There have been people that have tried to pass electricity through one bundle of wires for the purpose of spinning a magnet, and then use that spinning magnet to generate electricity on another bundle of wires. And you can do that, but their hope was to generate more electricity out of the second bundle of wires than they were spending on the first bundle of wires to spin the magnet. And there have been all kinds of attempts to make free electricity. It doesn't happen because there's friction here and the law of conservation of energy. You can't ever make more electricity than you have spent to create the motion. But lots of people have tried it. If you go on YouTube, lots of people claim to have done it, but they're wrong. This is a very, very big current generator. So this is a generator that would be like in a dam, and they would use water flowing down a channel in a dam to spin a water wheel, which then turns this massive generator to create a lot of electricity. And that is a way that, cities generate electricity. I don't think we have any hydroelectric projects here in Hawaii, do we?
No, I think we do.
We do have hydroelectric projects in
They're
Hawaii?
like in the ocean. They're like really small.
Oh, they're tidal turbines. Yeah, not dam turbines. So I was in Flagstaff where I lived. We were very close to,
Where do you live?
Flagstaff,
Where's
Arizona, northern Arizona. We were close to two huge dams. The Hoover Dam, which is the largest hydroelectric project in America, was about an hour drive away. And then the Glen Canyon Dam is another one of the top 5 largest hydroelectric projects in America. So we were close to 2 of them, and most of our electricity came from dam turbines as the water was running down these channels and spinning the wheels and making electricity. So this is a very large one. And then I've already said hydroelectric cars. Sorry, not hydroelectric cars. Electric cars. This is a hybrid being charged, and they're charging the battery. But then every time the car coasts or brakes, that energy of the spinning wheel is turned back into electricity to charge the battery again. So it regathers electricity from its own motion as it's going down the road to keep the battery charged. It's kind of cool. Okay? 2 kinds of electricity, 2 kinds of electric current, and the difference between them, you'll see in a minute, is principally in how it's generated. Is it a spinning magnet inside a fixed electrical coil, or is it a spinning coil of wires inside a fixed magnet? And there's a little bit more complexity to it than that, but generally speaking, there's 2 kinds of electricity. things. One, where in alternating current, the positive and negative poles switch several times a second. Matter of fact, several is not quite enough. They switch 120 times a second. 120 hertz is a common frequency. 60 hertz is another common frequency. But the poles switch several times a second. And it's produced when the magnet spins inside a fixed electrical coil. And that's the more common sort of generation. And alternating current is what we have in our homes and what we use most widely in power grids. There are some power grids that are DC now, but it's rare, and it's kind of a new technology to have a DC grid. Almost all the grids in America are alternating current, are AC, and it's produced by spinning a magnet within a fixed electrical coil. A direct current uses constant poles. So what's the positive is always the positive, what's the negative is always the negative, and that is created with a new kind of generator where we spin the wire inside a fixed magnetic field, and we use, it's not on here, but we use a broken loop to make sure the electricity doesn't switch poles. You'll see pictures in a minute, it'll be clear. But the poles are constant in DC. The poles switch in AC. Kind of a funny story, and I think I have time to tell you a funny story. Direct current generation was the first electrical generation. And when Thomas Edison was starting to sell people electricity to put in their homes, Edison Power Company was DC. And then one of his workers went to work for another guy, George Westinghouse. And because Thomas Edison's employee thought that alternating current was the better way to wire homes and sell electricity. And Edison said, no, we're DC. And so his employee left and got investing from George Westinghouse, a competitor. And Westinghouse Electric, using Edison's old employee's ideas, created alternating current power companies. So you could either wire your house for AC and buy electricity from Westinghouse Power, or you could wire your house for DC and buy your power from Edison. Competing markets. Westinghouse did not have the name recognition as Edison did. Edison, everybody knew Edison. He invented the light bulb, right? Or he oversaw the invention of the light bulb. And he was coming out with all kinds of electric things. Everybody knew Edison. Nobody knew Westinghouse. Everybody was buying power from Edison. Westinghouse's company was not doing so well. So Westinghouse thought, I'm going to destroy Edison Electric. So he brought a whole bunch of newspaper reporters. There was no television at the time, but he brought a whole bunch of newspaper reporters to his lab. And he grabbed a wire that was running a very low voltage of AC power and grabbed a light bulb with the other hand and lit the light bulb with electricity flowing through his body. And he told all of the reporters, see how safe alternating current is? This is what you want in your home. Well, he didn't tell the reporters it was only about 5 volts of electricity that he was passing through his body. If 5 volts DC would have been safe too, but he didn't bother to tell them that. He said AC is very safe. Then he took a whole bunch of rats and he wired the rats together. And he passed 10,000 volts of direct current electricity through them, and the rats exploded. And he told the reporters, see how dangerous direct current is? This is what Thomas Edison is selling you. This is what's in your house. The reporters went home and wrote their articles, and Thomas Edison's electrical company started to go downhill. And people were running away. Okay? And so Edison, oh, you know what? I'm sorry. I got that story backwards. Edison did that to Westinghouse. Sorry, I got that backwards. Edison did the rat thing, and he switched it. He held DC. DC is safe. That's right. Sorry. He blew up rats with AC current. Westinghouse's power started to go down. Sorry, I switched the stories. Apologize. Okay. Switch the story. So anyway, it's Westinghouse's power that starts to go downhill. Everybody's running away from AC because AC blows up rats. DC is safe. And then when Westinghouse's company had gotten to be almost bankrupt, Edison went and bought the company. He purchased Westinghouse Power. So he waited for the company to be very devalued. Then he moved in and he bought it. So now Edison owns Westinghouse Power. Then Edison waited about a year, and he took AC current off the grid. No more AC current. Everybody's using DC current. But AC current really is better for homes. But so he waited about a year, and then he invited the newspaper reporters back to his lab, and he said, I have reinvented alternating current power. It took a year, but I've made it safe. And then he connected himself to a circuit, just like he had done with the DC, and again, very low voltage, lit up a light bulb. See, everybody, I have fixed alternating current power. And then Edison Electric started selling AC current power. And now, Edison Electric still exists as a company. In many, many parts of the country, your power bill comes from Edison Electric. And Edison Electric is selling you alternating current. But he bought the technology when he purchased Westinghouse Power after he had destroyed the company with a smear campaign. So, it's an amazing story. And so Thomas Edison, he's a famous guy, but not always the most honest. This is a spinning magnet and fixed electrical coils. This is the more common way to generate alternating current. So what happens in this coil of wire is the north pole moves through and it generates positive power, and then as the north pole moves away and the south pole moves through, it generates negative power. So this current goes positive, negative, positive, negative, positive, negative every time the north or the south is facing it. But all three bundles of wire do that, so that it allows you to generate three sources of power from one spinning magnet. And the power will go back and forth between positive and negative current, depending on what's happening. This is a spinning loop of wire between a fixed magnetic field. And this is the more common way of generating DC power. The difference being that this little ring that gathers the electricity is broken. So this side of the wire passing through the magnetic field generates a positive potential. And then that same piece of wire goes over here and generates a negative potential. And so if this ring that gathers the electricity were uniform, it would still be alternating current, because it would make positive, negative, positive, negative. But because this loop is broken, this wire coming off of it only ever sees the side of the coil going towards the positive magnet, and so it only ever sees positive potential. And this side only ever sees the loop that's going towards the south, so it only sees the side of the loop making negative. And so this side of the brush and this wire only sees negative electricity. So you get a constant current of positive coming off of this wire and negative coming off of this one. So this is a DC generator, and this was an AC generator. This is the much more common way of doing it. Okay, this is what Edison came up with. This is what Westinghouse came up with. So there you go. Transformers. Here's an electrical device that you need to know something about. Transformers are electrical devices which use the relationship between magnetism and electricity to increase or decrease the voltage in a circuit. So when you look at the power lines outside, if you see power lines running along the street, those power lines carry tens of thousands of volts. In your home, running in your wall is either 110 or 220 volts. If you had a 10,000 volt wire coming into your house and you plugged anything into it, that thing would explode because it doesn't know how to handle that much power. But if we had wires running along the street with only 110 or 220 volts on it, the power would quickly be used up by home after home after home sucking off of that line. So in order to get the power to travel a long ways down wires and feed a large power grid, we need very high voltage in the wires, but we need relatively low voltage in your home. And so there was an invention of this device that takes really radically high voltage and gives you tiny voltage out of a wire. So it's it's just filtering off a little bit of electricity from a bigger source of power. And that's called a transformer. And these are not named, you know, like Optimus Prime and Bumblebee, and that's not what we name these. They're called step up or step down, not Optimus Prime and Bumblebee. I'm sorry.
I like Bumblebee.
Yeah, well, if you want to name a step up transformer as Optimus Prime and step down as Bumblebee, I guess you could. But step ups increase the voltage, so that takes a small voltage and creates a big amount of voltage. The step down is the opposite. It takes a big amount of voltage and siphons off a small amount of voltage out of it. So step up and step down transformers. And these transformers, they create a magnetic field from electricity and then use that magnetic field to make electricity. And we can either use it to create more or less voltage. Now, you're not going to make more or less amperage. So this is where you can't use these things to create free power. But you can use them to make more or less volts. Okay? And so I'll show you some pictures. A step up increases the voltage. A step down decreases the voltage. No, not that kind of transformer. Okay, here we go. I'm sorry. Here we would have a potential difference on one side of the circuit, and we wrap a bunch of wraps around a magnet, and this is a cubic magnet. This piece of steel is a magnet field, and the passing electrical current through one set of wires creates a magnetic field, and the magnetic field then creates a current in the second set of wires. So you can either use a few number of wraps, so low electricity, to create more voltage on the other side, or you can use more wraps, more voltage, and fewer wraps to make less voltage. The relationship between the number of wraps on the opposite sides of the magnet is the relationship between the voltage. So if this were like 100 volts with 2 wraps, and then you were to wrap 4 wraps around the other side of the magnet, the relationship of 2 to 4 would be the same as the voltage, 100 to, what would it be? 200. Yeah. So the number of wraps proportions is the number of volts proportions. The amperage will not change. The amperage will be the same, but the voltage will change. So you'll get proportionally how many wraps to the 2 sides. So if you want to step up, fewer wraps going in, more wraps going out. If you want to step down, more wraps going in, fewer wraps going out. There you go. Here's another picture of a transformer. So here's my square magnet, and I have fewer wraps on this side than on this side. So depending on where the power is going, if the power is coming in here and going out here, then it's a step-down transformer. If the power is going in here and coming out here, then it's a step-up transformer. Okay? This is a very, very large transformer, and you can see all the wraps of wire, and the magnets are actually inside the box here. But this is a huge commercial transformer that's taking thousands and thousands of volts and turning it into very few volts for distribution to homes in a power grid. Okay. And this is what a smaller transformer in a neighborhood. Huh? Yeah. So this is a transformer on a power pole. So this is like a central transformer at a power grid generation station. This would be a smaller transformer that would feed off lines to individual homes. Okay? These things sometimes explode, and they go bang really bright and bang really loud, and they can cause fires when they fail. If this were to ever go boom, it would shake a neighborhood. It would be a big time problem. These are much more carefully maintained, but sometimes these things still go and they can cause fires. So be gentle if you ever see a power pole down in one of these within reach. No touchy. Those are some pictures of transformers. There you go. Oops, just kidding. Last slide. Yeah, last slide. Electromagnetism can also be used for some other things. Magnetic storage media. So if you have jump drives, that's an electromagnet. And that's kind of what Josiah was asking me about. If you take a flash drive and put it by a big magnet, does it screw your flash drive? Yes, it does. Because inside that storage media, it's actually stored with magnetic fields. And it's the arrangement of the magnetic fields that is the information. So if you bring a big magnet to it and you screw up the arrangement of that magnetic field, change the magnetic field, then you have changed the data and you've lost the data. That used to be the way that people would, back in the day when there was such thing as magnetic tape. We don't have, cassette tapes that we store music on anymore. But that used to be a big deal if you were to take your cassette tape with your new album that you just bought on it and accidentally expose it to a big magnet, then that album would be wiped off of the tape. And if you really hated somebody, you could bring magnets over to their house and put it where they keep their cassette tapes, and then their songs would go away. But that's not something that happens much anymore. But still, it's a magnetic thing. It's used for storage media, flash drives, hard drives, any kind of magnetic tape, which more and more doesn't exist anymore. Particle accelerators, these are research tools that take very small pieces of matter, usually an atom, and use magnetic fields generated by large amounts of electricity to fly those atoms into each other and make small atomic explosions, and watch what happens when the explosion happens and learn about matter that way. Particle accelerators are some of the most expensive electronic tools that science has, and more and more of them are getting built around the world as we start to study the atom more. Railguns used to be a thing of fiction, and now they exist. The newest generation naval vessels have railguns on them. And they are just beginning to be put into live-action warfare. Only a couple of actual functioning railguns exist, but more and more that probably will be the way of the future for launching things long ways. And then magnetic trains, specifically more of them in Europe and in Asia than in the States. For some reason, the States haven't picked up on the magnetic train as quickly as other places have, but I've ridden them in Europe. It's amazing. The train, it's on the ground while it's being loaded, and then they turn it on and it floats, and you feel it come up like an inch or two, and then the ride is just like butter. There's no bumps. It's just smooth and it's fast and it's awesome.
Where do they have it in the US? Nowhere?
I don't know if they have any in the US, to be honest with you. I rode mine in Belgium. So. Yeah, and they go crazy fast because there's no friction. There's only air resistance. There's no wheel friction. So they go stupidly fast. The train I was on was doing about 180 miles an hour. So you look out the window and there's this massive thing full of hundreds of people doing 180 miles an hour, and stuff is just flying past you. It was so cool. So cool. I don't know why the US doesn't make them, but we don't so much. This is a hard drive. And this is a very, very complicated magnetic system. And this little arm that floats over the hard drive is seeing the magnetic signature and interpreting that as information. So that's what a hard drive is. Obviously, SD cards are just a smaller, simpler, no moving parts version of that. This is a particle accelerator, and you can see it in an aerial shot. This is the city of CERN in Switzerland. And this huge loop is a long magnetic pathway. And then it starts, the generator is here, and they will send a signal out through this part of the loop, and they'll send the signal out through this part of the loop, and then they will turn a corner and collide with each other back at the generator. And a small nuclear explosion happens in this building. But it's very small. It's one atom destroying one atom. So it doesn't destroy the city. But it's a very small nuclear explosion, and then they can watch the parts of the atom fly apart and see what was in the atom and learn about the nature of the atom from it. But if you look inside a particle accelerator, it's just a whole bunch of electromagnets, and they get particles very close to the speed of light, and then run them into each other. So kind of cool. This is an actual railgun on a naval vessel, and so the Navy admits that they have them. For a long time, it was a secret, but it's only on the newest class of attack ships, and I think there have only been 2 built. But the cool thing about a railgun is it uses electricity, not an explosion, to drive the projectile. So as long as the ship has power, which it has because it has a nuclear generator, you don't ever run out of the ability to throw something, right? And so, and you can throw it a lot further, and it's a lot cheaper. So the old kind of shell, if you've ever seen the kind of shell that a battleship fired, right? The shell is about 4 feet tall, and the slug that it fires is about half of that. And then the other half of that, 2 feet tall and about a foot in diameter, is black powder that explodes and drives the projectile out of the gun. That costs a lot of money, right? And it's also very dangerous to store. Imagine if a battleship gets hit in its magazine with all of this black powder stored. Ship is over because all that black powder goes away and the ship is blown into pieces. So the way to destroy a battleship is to hit the magazine. If the guns are rail guns, there's no black powder involved. You have the slug. You load the slug and magnets throw it at your enemy. And so if this ship gets hit in the magazine, nothing explodes because all you're hitting is a bunch of lumps of aluminum, not nothing that goes boom. So it makes the ship much more survivable. The ship can take a beating without blowing itself up because there's no black powder anywhere in the ship. So that's the main advantage. The other advantage is you don't run out of black powder because you don't need any. You can still run out of slugs. You can still run out of big pieces of aluminum to throw at each other, but you're not going to run out of the projectile part of it. And then it's a lot safer. You can stand next to this gun, and it can go off, and all you're going to hear is the of the electricity moving down the gun. You're not going to lose your hearing or get thrown to the side. Whereas if you stand next to a battleship when it fires and you're anywhere near that cannon, your hearing is done. You may have been thrown into the water because it's a percussive bang that goes off. So it's a lot safer for the ship and still gets to destroy the enemy. So that's a real gun. Of course, this is a maglev train. This one is in Japan. I rode on something similar in Belgium. But what's cool about it is the track is an electromagnet. The train is an electromagnet. And so the train is attracted to the magnets slightly in front of it and repelled by the magnets slightly behind it. So the track changes polarity as the train approaches and as the train leaves. So the track is pulling the train and then pushing the train, and it gets really fast. And because it's not touching the rail anywhere, there's no friction to the rail. There's only air resistance. So if you build it nice and sleek, then there's very little friction involved at all, and the train goes way fast. Yeah. That's a cutaway, so you can see the way it works. But I think they took a photograph of one passing and then superimposed on the image, so you can see how the thing happens. So, but there you go. Electromagnetism, pretty cool. Any questions? Awesome.